Welcome back, physics people. This is Mr. Havens again. This time we're going to continue with velocity versus time graphs, and then we're going to talk about the kinematics equations that are very important to this unit. We've already seen them in our math review, but now we're going to talk about them and what they mean, and then we're going to start to put that together, and we'll do some examples and stuff, not in this PowerPoint, but in class and in some other PowerPoints. Alright, so here's a velocity versus time graph. As you can see, this velocity, the slope of this graph is at a constant velocity or a constant acceleration, because the velocity versus time graph is moving linearly. At 1 second, it's at 4 meters per second. 2 seconds, 8 meters per second. So this person, vehicle, whatever it is speeding up and accelerating at the same time. So as velocity increases, so is acceleration. So the slope of this graph tells us the acceleration of the object. So that's what's important about a velocity versus time graph to us, being able to read this and being able to tell what they mean. So the slope, as we talked about in our last PowerPoint, is the rise over the run, or the change in y over the change in x. So if you didn't already know that this is y and this is x, you should by now. So rise over run. So this is the run, this is the rise. So rise over the run. So here's another velocity versus time graph. I told you that the slope is equal to acceleration, which is also equal to a change in velocity, because that's what our y-axis is, over a change in time, what our x-axis is. So using this graph, I can simply give you a graph and say, tell me what the acceleration of this object is. So in this case, we have a change in velocity from 8 is our final velocity over here, minus our initial velocity, which is 4. So 8 meters per second minus 4 meters per second gives us a change in velocity of 4 meters per second over our change in time, which was 4 minus 2, so 2 seconds. That would give us an acceleration of 2 meters per second squared. And so those units are important, the meters per second squared for acceleration. And it has a direction, so in this case we would say the acceleration is 2 meters per second in the positive direction, because acceleration is a vector quantity. Sometimes we have to describe the motion of velocity versus time graphs, or position versus time graphs. We'll work on the position versus time graphs in the lab in class, but on here I want to explain the velocity versus time graphs because they're a little bit harder to explain sometimes. So if I picked point A, actually I'm going to have you try to describe what you think motion would cause each of these, like moving forward, moving back, constant, whatever. So like I'll give you an example. From A to B, I have increasing velocity, and since it looks like it's fairly constant, because in 1 second it went 10 meters per second, and in 2 seconds it went 20. So that would be a constant acceleration. So constant velocity and constant acceleration. Well, actually it's not a constant. Increasing velocity and constant acceleration. And then from like B to C, I have a constant velocity at 20 meters per second and 0 acceleration. So now you try to describe the rest of the graph. I'll give you a couple of minutes here. So go ahead and pause the video. Try to describe points C to D, D to E, E to F, F to G, and G to H, and then I will go over them. Alright class, now you've probably had time to go over this and you should have paused the video. If you didn't, go ahead and pause it now before I go ahead and give the explanations. I want you to try this on your own, try to figure it out, and then we'll talk about it. So then from C to D, I have increasing velocity again, because as we can see, my velocity is going upward, and I have acceleration, because if I have increasing velocity, I must have acceleration. So I'm increasing in the positive direction. From D to E, I have constant velocity again. It looks like this B to C here. So therefore, I have constant velocity and no acceleration. So when the velocity is constant, like when we're in cruise control, we're not accelerating. So think about when you're in your car and you're driving and you're going on a long trip and you drive up to 65 miles per hour and you hit the cruise control and it stays there for 2 hours. You're not accelerating, but you do have positive velocity. It's just constant at the same speed or the same velocity. From E to F here, I still have a change in velocity, except now it's in the negative direction. So this is almost like jamming on the brakes. I'm driving along, I jam on the brakes, so I'm accelerating in the negative direction or decelerating, but I still have an acceleration. I have a negative change in acceleration. So I'm decelerating in this case. From F to G, once again, we're at a constant velocity at 20 meters per second, so we have no acceleration. And then from G to H, I have an increasing velocity in the positive direction, and I have a increasing acceleration, or I'm accelerating in the positive direction. And that's how I would describe this graph. We'll do more graph explanations in class, but this is just kind of a start to tell us how they work. So we got to get to the kinematics equations. This is really the meat of this unit. This is what we really need to know. We really need to understand to calculate things. So average velocity is the total displacement divided by time. So to write that equation, you put V average, or velocity average, is equal to change in displacement, the delta D, divided by the change in time. That is average velocity. So if I say that Mr. Havens got in his truck, he drove 720 kilometers, it took him 2 hours to do so, you can then calculate the average velocity of my trip. So in that case, I would have traveled 360 kilometers per hour because it was 2 hours and 720 kilometers. Not realistic, but that's how we would do it. Velocity, to find it, is equal to a change in displacement over a change in time. And we would write, whoop, where did our equation go? We did not put our equation there. Sorry about that. So we'll talk about that in class. Well, that is the same equation, just written out in words, and that's what your star chart will look like. So now we're going to have an example problem, and it's going to show how we would use this. So if Mr. Havens gets in his truck, drives 400 kilometers east, it takes him 5 hours to do it, what is his average velocity? So like the method I showed you called the guess method, we write down our givens. Displacement is 400 kilometers. Time is 5 hours. Our unknown is we want to know the average velocity. The equation we're going to use is the one we learned earlier. Velocity average is equal to change in displacement over change in time. So our average velocity is equal to 400 kilometers east divided by 5 hours. That's our time. And that gives us an average velocity of 80 kilometers per hour east. Don't forget the direction, because this is a vector and it needs a direction. So that's how we use our first kinematics equation. That's the easiest one to use. Our second kinematics equation is acceleration, that's the A, is equal to velocity final minus velocity initial divided by time. So in words, same thing. Acceleration equals velocity final minus velocity initial divided by the time. So acceleration is, once again, a vector quantity that measures a change in velocity over time. So it has to have a direction with it when we give an answer. So we're going to do an example here. If Mr. Havens is driving, if Mrs. Havens is driving Mr. Havens F-250 and she accelerates from a stoplight to a velocity of 80 meters per second west, and it takes her 5 seconds to do so, what is her acceleration? Once again, we'll use our guess method and write down our givens. Our givens are initial velocity is 0 meters per second west, and you say, well, how do I know it's 0 meters per second west? It doesn't say that in there. But it said that she accelerates from a stoplight, which means she started from rest. So our initial velocity is 0. Her final velocity, because she accelerated from a stoplight to a velocity of 80 meters per second west, is 80 meters per second west. And our time, as we told you, it said it takes her 5 seconds to do so. Time is equal to 5 seconds. Our unknown is we want to know the acceleration. So we write down our equation, and our equation is acceleration equals velocity final. So acceleration equals velocity final minus velocity initial divided by the time. So now substitute in our information. Acceleration equals 80 meters per second west minus 0 meters per second west divided by 5 seconds. So if you get 80, because we have 80 minus 0 divided by 5, that gives us 16 meters per second squared. And we should have west on there. Mr. Havens made a mistake. We have to have our direction. So it's 16 meters per second squared west. That's our acceleration. The next equation we're going to come to is also for acceleration, but it uses different variables this time. You still see we have acceleration, but now we have velocity final squared minus initial velocity squared divided by 2 times the change in displacement. So now instead of time down here, we have change in displacement, and we square both of these. So written out, acceleration equals velocity final squared, as you can see here. Velocity final squared minus initial velocity squared times 2 or divided by 2 times the change in displacement. So acceleration equals final velocity squared minus initial velocity squared over 2 times the displacement, change in displacement. We're going to do an example with that. So if Mr. Havens drives south from his house with an initial velocity of 10 meters per second, say north, since I didn't put in a direction, I apologize again, and accelerates to a velocity of 20 meters per second south, so I guess our 10 meters per second should be south to keep it the same, over a displacement of 10 meters south, what is his acceleration? So my givens are my final velocity is 20 meters per second south, my initial velocity is 10 meters per second south, and my displacement is 10 meters south. So my unknown is acceleration. My equation is acceleration equals final velocity squared minus initial velocity squared over 2 times the change in displacement. I substitute in acceleration equals 20 meters per second south squared minus 10 meters per second south squared divided by 2 times 10 meters south. And if you work out all that math, it works out to 15 meters per second squared south. Because I would have had 400 minus 100, leaving me 300 divided by 20. If you don't understand it, we'll talk about it in class, and I'll work over this. The last kinematics equation we need to learn, it's the hardest one, but it's usually the easiest one to operate, and you'll understand why once we do some examples. So my change in displacement is equal to my initial velocity times the change in time plus 1/2 acceleration times time squared. So we're going to write that out in words. So change in displacement, as you can see, equals initial velocity times the change in time plus 1/2 acceleration times our time squared. So that little star means times something if you did not already know that. So here's our example. If Mr. Havens is driving home from Lubbock Cooper High School and it takes him 20 minutes to get there, what is his displacement if his initial velocity was 5 meters per second north and his acceleration is 12 meters per second squared north? So once again, we'll use our guess method. We'll start out with our givens. Time is equal to 20 minutes. Initial velocity is 5 meters per second north, and acceleration is 12 meters per second squared north. What we want to know is our displacement. So now we need our equation. Our equation is displacement is equal to initial velocity times the change in time plus 1/2 acceleration times time squared. So now we're going to substitute. So our displacement is equal to 5 meters per second north times 1200 seconds, because I took 20 minutes, and if you notice I need to convert that to seconds. We'll talk about that in class if you have problems with that. So 5 meters per second north times 1200 seconds plus 1/2 times 12 meters per second squared north times 1200 seconds squared. So then after I do all that fun math, I would have traveled 8,646,000 meters. So meters, that's a lot of meters. Is that realistic? No, it's not that far to my house, but we're working on the math. So, and if I wanted to convert that to kilometers, I would divide by 1,000, and it would have been 8,646 kilometers, which is a long ways. But just for the sake of the math, let's get this done. And this, I believe, is the end of our lecture, and we will talk about the rest in class. Thanks for your time.